Hey, everybody, thanks for coming. We're going to get started in probably just about 1 minute. We're going to let folks filter in. All right, thanks everybody for coming. I know that folks will be filtering in over the next few minutes. I am Allison Schwartz. I am one of the co-chairs for the Quantum Working Group here at ATARC. We are so excited to have our speaker here today. As part of the working group, what we're looking at doing is helping educate folks on what can be done with quantum technologies. Today, because it's the first question many of us get is quantum is really cool, but what can it do? And so I want folks to know that we will be having Q&A at this, but during this event, but you can actually type in your questions in the chat and we'll get to those as we move forward. And we ask folks to keep muted for the presentation, and then again, we'll move into the Q&A as well. We are so excited to have Thomas Phillips here. He is the founder and chief technology officer at Ridgeback Network Defense. He has a long career, over 24 years in the cybersecurity space and in the intel world, and came from military. And I've heard some of what Thomas has said and some of the work that they're doing on how they can look at adopting quantum computing for cybersecurity. And so with that, I will turn it over to Thomas. And again, please put your questions in the chat and we will get to them throughout the process. But thank you so much, Thomas. Over to you.
Hi, I'm Tom Phillips, the CTO of Ridgeback Network Defense. We make a cybersecurity product called Ridgeback. And today I'm going to talk about how we're exploring quantum computing for cybersecurity. There we go. This talk's broken down into 3 parts. First, I'll describe some of the problems we come across in cybersecurity. Second, I'll briefly discuss why these problems are extremely hard to solve with classical computers. And third, I'll go over how we can leverage quantum computing to make the problems more tractable. Part 1, domain problems. I could tell you my adventures beginning from this morning, said Alice with a little timidly, but it's no use going back to yesterday because I was a different person then. At Ridgeback, we reject the idea that pure analysis will improve computer security. A purely analytic solution leads to a cat and mouse game. A cybersecurity solution needs to have teeth. Rather than viewing cybersecurity as a data analysis problem, we see it as a game, like chess, but much higher stakes. The adversary makes moves and the defender makes moves. Each opponent is trying to outwit the other. The important point is that we dynamically alter the environment by injecting custom-crafted Ethernet frames. The net effect is that an adversary's actions become very noisy and easy to detect. We're able to isolate the adversary in a way that they can't detect what's actually happening. To keep track of the whole system, Ridgeback converts real-time data streams into graph data structures. A graph has nodes and links, which are formally called vertices and edges. In general, nodes are things like computers or pieces of executable code, and links are whatever connects the nodes. For example, computers might be connected by network cables. Small graphs are easy to work with, but large graphs, the kind we use for production IT systems, bring about many difficult problems. So now let's talk about the hard problems. It takes all the running you can do to keep, and sorry, you can read it. Ridgeback observes many network events in real time and also injects its own custom data into the network. In the case of production networks, this results in very large graph data structures. A production network may host thousands of endpoints, and endpoints anything on the network that's addressable, like a thermostat, a computer, or a network device. Even worse, those endpoints may communicate with one another across tens of thousands of links. Processing these large data graph structures takes immense compute power. In fact, while smaller graphs can be visualized, very large graphs can be completely indecipherable due to their complexity. Despite their complexity, we still need to understand what is happening in the graphs because we need that information to make decisions about how to shape the environment. Because remember, it's like a game. The adversary is taking moves and then we make moves. We're trying to anticipate what they're going to do. For small graphs, a human operator can pick through the data and look for clues about what is happening. For large graphs, that's impossible. So we have various graph theory algorithms that give us insight into the underlying structures hidden in our giant hairball graphs. Unfortunately, many of the graph theory algorithms are expensive. Let's call these the hard problems. One example of a hard problem is finding the minimum vertex cover. That problem is like deciding where to put the least number of cameras to cover the maximum amount of area. On a network with 10,000 nodes, we might expect a minimum vertex cover algorithm to take around 6 times 10 to the 100 steps to find a solution. That's a number with 101 digits. To put things in perspective, there probably are no more than 10 to the 82nd atoms in the universe. That's a 1 followed by 82 zeros, and it is much, much smaller than the number of steps we need to solve our hard problem. To solve our hard problems, we need a way to go faster than traditional computers. And so now quantum computing. And the quantum computing part that I'm going to talk about here is 2 parts. First, I'm going to talk a little bit about the traditional gate approach, the quantum gate approach, and then I'm going to show you what we've done instead. And again, more Alice in Wonderland, because quantum computing sometimes feels like this. The quantum gate model of quantum computing, as we recognize it today, evolved over the 80s and 90s last century. The most significant developments were, one could argue, Peter Shor's algorithm in 1994, the various internet technologies in 1995, and Love Grover's algorithm in 1996. Peter Shor's algorithm provided evidence that modern cryptography could be cracked using quantum computers. The internet technologies of 1995, such as Windows 95, Amazon, Yahoo, and others, brought the promise that everyone could use the internet for commerce as long as there was strong cryptography. And in 96, Love Grover's discovery of a quantum search algorithm led many people to think that quantum computing was going to start advancing pretty quickly. It was just a matter of time before we all had access to some super cool quantum computers. While the promise of quantum computing was really exciting, there were some people who were feeling a bit anxious. I was one of those people, actually, at the time. The primary application for quantum computing at the time was breaking codes, and strong cryptography was what was holding the world together. The promise of e-commerce needed strong cryptography, and nations depended on strong cryptography, crypto, to safeguard their diplomatic and military secrets. It looked like something big was on the horizon, and it was just a matter of time. It's been nearly 30 years now. Technology's been moving faster and faster. Quantum computing must be easy now, right? I have a bunch of really hard problems to solve. This is not research. They're real problems in cybersecurity that are holding back product features. They're the graph problems that I described earlier. Quantum computing has been cooking for nearly 30 years, so something must be viable. Let's get our software development team quantum ready and start tackling these problems. So I'm going to start describing now what I had done a few years back to look at the quantum technologies that were available. And then after these, I'll show you what we actually decided on. So step 1, all the developers need a solid working knowledge of linear algebra. They need to understand vector spaces and matrices. They need to understand unitary matrices and reversible functions. A good background in functional programming would help. They need some basic understanding of Hilbert spaces and complex numbers. To grasp the difference between the inside and outside of qubits, they need an understanding of eigenvectors. Finally, they need to have a good grasp of using matrices as operators and feel comfortable with bracket notation. Step 2, the developers, the development team that's writing the software, they'll be working with quantum gates. And they need to be able to apply their linear algebra skills to get a handle on superposition, which is the heart of quantum computing and the reason quantum gates work at all. There are a bunch of standard quantum gates they need to understand. Unfortunately, a background in logic will only get them so far. Once we start putting qubits into the gates, things get really weird with entanglement. It's one thing to say a cat's both alive and dead, but something altogether more complex when we start talking about functions that mathematically encode a small herd of cats whose gates are all, or whose fates are all intertwined. Oh yeah, and there's another small detail about quantum gates. They're all custom built. There really isn't such a thing as a generic standard quantum gate implementation. The hardware really matters. It matters a lot. It matters so much, in fact, that we need physicists. One moment, I lost my place. I apologize. All right, physicists. Step 3 is making sure we have some physicists on hand. They could be consultants, but we will definitely need someone around who has a strong hands-on understanding of quantum mechanics and experimental physics. On a good day, systems that use quantum gates will behave strangely. That's the nature of a quantum computer. Unfortunately, any quantum computer, by its very nature, is a very delicate instrument that requires expert care and feeding. When things go wrong in the quantum computer, you will need experts to call on. Finally, we have step 4, luck. Qubits in superposition and entangled qubits have incredibly short shelf life. Without extraordinary protective measures like extremely low temperatures and significant shielding, the qubits will collapse and become useless. That collapse is called decoherence. Even with the strictest of controls, the most well-protected qubits can still collapse. If you're lucky, then the system can produce an answer you like. If you're not lucky, then try again. And I almost forgot step 5. We need some quantum algorithms. However, in 2003, this is what Peter Shor wrote about quantum algorithms. Many people expected a succession of other interesting algorithms to follow. The reality has been disappointing, especially compared with the progress of the rest of the field of quantum information processing. And unfortunately, quantum algorithm development is still going pretty slow. Today, there are generally 3 types of algorithms that work well with quantum gate solutions. Even after all the time and effort we might spend getting our team ready to work with a quantum computer, our best classes of algorithms will find a frequency, find a number, or find a random destination. None of these seem like a good choice for our hard graph problems. And I imagine some people might take offense, but I'm going to go out on a limb and say that solving most real-world problems with quantum gate solutions is not practical. It all makes for great research, and there are clear applications for cryptography and time series analysis. However, we need to look somewhere else for solutions to our hard graph problems. Fortunately, there's some light at the end of this quantum tunnel. Quantum gates are not the only game in town. There's another approach to quantum computing using a technique called quantum annealing. I found out about this a number of years ago. Like traditional annealing, we heat up a system and then let it cool down. And when it cools down, it will be in a state that we like. Instead of heating metal, we put qubits in a state of superposition and set up constraints between the qubits. I won't go into the details of how this works, but if you're interested, I recommend reading up on both adiabatic computation and quantum annealing. And let me go backtrack just a little bit. Superposition, this core concept in quantum computing, is about what we would normally think of as a bit, which is a 0 or 1, can actually be in this indeterminate state. It can be both 0 and 1 at the same time until you look at it, until you read it. It turns out that quantum annealing is a good method for solving problems structured as an Icing model. The Icing model is a convenient framework for talking about ones and negative ones and the constraints between them. By the way, anything that talks about ones and negative ones could also be talking about ones and zeros. For example, that's an alternative form to write these problems in. Think of something like a magnet where every part of the magnet is pulling or pushing on every other part of the magnet at the same time. It's a problem that's very hard to solve when there are many parts. The Icing model can describe the problem, and quantum annealing is good at solving Icing model problems. Let's look at one of these problems to get a more concrete idea of what we're talking about. So there's a little bit of math here. I hope it's not too bad. So we have the H equation in the upper left there. The H, A, and B is 3 plus 2AB minus 5B. And so the variables are A's and B's, or the A and B, and an A and a B can be either -1 or 1. A Hamiltonian is a mathematical expression that represents how much energy is in the system. And that's why we use H there for Hamiltonian. Remember that part about cooling down the system? We want to know just how low the energy of a system we can get. If we have to try all the different combinations of variables of A and B in this equation, then that's 4 steps, assuming we just brute force it. Quantum annealing can try all 4 possibilities in 1 step. Why is that important? Because let's say we have 1,000 variables. Quantum annealing can try all 2 to the 1,000 possibilities in 1 step. And that's a pretty awesome speed up. Okay, it feels like we've strayed away from our hard graph problems. There's a clear connection though. Quantum annealing is very good at solving these special algebra equations. If we can turn our hard graph problems into simple algebra equations, then that means we can use quantum annealing to solve our hard graph problems. Even better, the math behind an Icing model equation is very simple. It's straightforward. That means our whole developer team will be able to easily understand what's actually going on. In 2014, Andrew Lucas wrote a paper that described using formulations for a lot of hard problems, a lot of hard computer science problems. Lucky for us, he showed that there are Icing formulations for a number of hard graph problems. We now have a clear way to map from our hard graph problems to Icing formulations. All we need is a system. All we need is a system that will do the quantum annealing. So the paper that he wrote, he showed how there are standard problems in computer science, like some of them that we have, the graph problems, graph analysis, and how you can translate those problems into an Icing model problem. And that's where we enter the DWave. The DWave computer is essentially a quantum annealing system, and that's exactly what we needed. Even better, the DWave comes with software libraries called the Ocean software stack. The Ocean software stack includes lots of very convenient libraries, like the DWave Network X library that includes function calls for solving hard graph problems. So the significance of this is that it's an API that a software development team can write to. They don't have to know the physics. They don't have to know any of the details of what's actually going on. They can write the problem. They can write the code to solve their problem in a way that they understand it. In this case, as a graph problem. So stepping back a bit from it all, we have a bunch of IT systems that need defending. We have an interactive cybersecurity software that uses graph data structures. The hard graph problems can be translated into Icing model problems. And the Ocean software stack, which is a collection of programming APIs, it abstracts away the Icing model details. It hides the fact that we're doing quantum annealing in the first place, and it lets us write simple Python code that solves our hard graph problems. And that's definitely practical. So are there any loose ends that need to be addressed? And yes, but they come from the hybrid aspects. So first, latency is an issue if there's a wait time for a limited hardware resource, like a quantum annealing system. Fault tolerance and failover are an issue if there are not multiple hot spares of the hardware resource. Security is an issue if the hardware is a shared resource. And finally, cost includes everything, including mitigating the risks of latency, fault tolerance, and security. And at the end here, I have a bunch of links. I've tried to go through this stuff very quickly because we only had 30 minutes and I wanted to leave time for questions. So on to questions, I guess.
Thanks so much, Tom. Really appreciate it. That was a lot of really great information. As Tom mentioned, he is available for questions for folks. So you can unmute yourself or put your question in the chat. I saw Marvin, you went off mute. So if you want to jump in with your question first.
Yeah, I noticed you weren't hardware specific, or I guess you were hardware agnostic, I guess. Do you favor a certain physical implementation or think one has a stronger chance than another?
Right now, the only working quantum annealing system I know of is the DWave.
Okay.
In terms of a quantum annealing. There are simulators out there. There are some FPGA simulators out there. There's a number of algorithms that could be used for different applications. The problem when you simulate it is that there are it tends to exasperate irregularities or eccentricities in the data set. So if you have what you think is a good quantum annealing simulation or simulator written in traditional software, there are going to be areas in your data set that it will not perform well at all on. There may be some areas where it does perform well, and it's very hard to know beforehand where it's going to do well and where it's not going to do well. So with regard to specific implementations, again, the DWave is the only physical quantum annealer that I'm aware of at this time. If there's others, let me know.
Thank you.
I have a question for you, Tom. One of the things with cybersecurity, especially, when you're looking at network threat detection or you're looking at, camera angles at airports and things like that, it's sort of like finding that needle in 1,000 haystacks. How are you guys kind of tackling that, given kind of traditional cybersecurity software that's out there, and how does quantum play into tackling, that you have to be 100% right versus not just 90 some odd percent right?
So, I'll talk about the cybersecurity domain that we're in. The way our system works is it's an interactive system. So traditionally, back when I invented the stuff that's in it that makes it work, it was taboo to inject data into the network for security. Monitoring things and analysis was the only well-accepted method for security. And it turns out that when you inject certain things into the network, it changes the game completely. And it's not just, so for example, some people say, well, we could put honeypots out there, and it's not just, it's not setting up something to trick people, it's actually changing the environment. So that you can actually remotely crash tools and stuff. So part of what we do is man in the middle attack. So let me step back a little bit. A broader issue that we face right now is that we have a large production network. Let's say it's got 10,000 nodes in it, and there are certain structures in this graph, and we need to know what parts we need to be modifying in the environment. What if we're going to change state on an endpoint, if we're going to inject certain data into certain network links, and to know where to do that, we need to, again, we have to understand the underlying nature of the, I'm trying not to go into secret sauce details or anything, but we need to know where to do that efficiently, because with 10,000 nodes, you have an enormous number of links, and the links are changing in real time all the time. And it's not tractable to just simply spam the entire network with lots and lots of data to try things. You need to be selective. And so at its heart, it's an optimization problem. At its heart, it's this problem of where do you need to apply your resources? So for example, the vertex cover, where to put cameras, that sort of problem. I use that example here. That's one example. I don't know if this answers the question. I'm kind of wandering.
No,
Sorry.
it does. It does. Thank you very much. I appreciate it.
Okay.
We have about 6 minutes left. So if there are other questions, folks can go off mute and ask questions.
Actually, I was wondering, what's the biggest network you could already address? I mean, did you do any kind of small scale test to see what's going on? Maybe I didn't understand well, but my feeling, I got lost a little bit just at the end. So did you apply it to real cases with smaller network to test it, or it's just theoretical work at the moment?
So Ridgeback is real, and it actually scales. There's no practical limit for the scaling for it.
No, but I mean,
it's a scalable architecture.
Well, yeah, but the problem is more the computer. I mean, we know that the DWave computer has still some limitation. I mean, the number of qubits and the, how big it can be. So what I was wondering is, I understand that you could have very, very large networks, but did you apply this to smaller networks which you could actually use the quantum, the DWave computers to solve and to see real results today, or it's still work in progress, basically?
So that's a work in progress. The latest one is about 5,000 qubits. There's the interconnectivity of the latest one. I'm not a DWave person, so I won't speak on behalf of DWave, but there's interconnectivity constraints in the DWave. The latest round is much better than the last one. I forget the actual terms. I think the DWave 2, is that the latest one?
No, we're at the Advantage, which is 5,000
okay.
5,000 qubits with 15
Okay.
connectivities, and the one
Right.
before that was 2,000 Q.
Right, with only 6, right, for the connectivity, right? So that connectivity is a constraint, right? And so that means that you can't necessarily use all 5,000 qubits the way you want to. It will be constrained somewhat by the interconnectivity. And then there's another constraint from the translation from the graph to the Icing model, right? So let's say we have a network with 10,000 nodes and many links, then that means that you can segment the problem and run parts of that on a hardware device or in a simulation, for example, but you can't run the whole thing. I don't know, I'll prognosticate. I think it's an engineering issue. Yes, there's a lot of research there that needs to go into how do you get a great number of, let's say an extensive amount of connectivity while increasing the number of qubits. How do you do that? But again, I don't speak for DWave. Does that, again, I'm kind of meandering, but.
Yeah, I mean, it somehow answers, I mean, but my question was really, couldn't you take a much smaller network and implement a real case scenario, you know, like a toy model, but not completely toy model. I mean, a toy model with 5 nodes would probably not be interesting, but maybe you could design a toy model with, I don't know, a few hundred nodes, which would already be very hard to solve with a classical computer, and then you could apply the DWave computer on this kind of toy model and see how it goes. So that was really my question. You know, a kind of demo, a toy model, which you could use with the existing quantum computer, not only thinking in the future.
Oh, right. So I mean, you could do real things right now on the DWave, for example, with the Ocean Stack. So let me go back. Oops. Let me go back to. So in the bottom right here, the simple programming. So this actually works right now. You can take let's say a minimum vertex cover problem, encode your graph data, and submit it up to the DWave in a batch job, and then get an answer back or get a set of results back. And that works now. And right, but where I'm at is this part, right? So everyone talks about, you know, this hardware is great and that hardware is great, but from a practitioner's perspective, there's a lot of real nuts and bolts practical things that you've got to take care of no matter what, whether it's a quantum solution or some other accelerator or whatever. And those big ones are the latency, fault tolerance, security, and cost. So let's look at latency, for example. So let's say you do have some kind of a hardware solution. It's out of necessity, it's probably going to be an expensive hardware solution, and there's going to be multiple needs for it, right? Multiple people want it. So the latency is specifically how long do I have to wait for my turn on that system? I don't know if anyone's around for the old mainframe days, but the time sharing system where you'd have a batch job and you'd submit it, and you might have to wait a couple of days for it to come back. And I don't know that it would be that bad, but if suddenly everybody jumped on the bandwagon and said, hey, we want to submit our jobs, then you're going to have a queuing problem. So then you're like, well, maybe I need to bring my own computer in-house or my own hardware resource, whatever it is. Then you need a place to put it, and then you're in it might be easy and cheap to maintain, but a lot of places don't necessarily have the facility to do that. Maybe you're in a remote location. Maybe you're airborne. Maybe in an aircraft. You could be anywhere. So that's not always an answer. And then fault tolerance. What happens if the link goes down? What happens if the machine goes down? And these are problems that we had in the mainframe days when we submitted batch jobs. So it could be, now you need a second one that's always there, your hot spare, or maybe a third. Maybe you need geographic place. Like now we have data centers, cloud providers have data centers all over the world so that you can hit the servers that are close to you. That's an issue. And then security. So let's say I'm sharing my compute resource with somebody else. Well, the data, I can speak for my company and the customers we work with, they do not like the idea of their data going off somewhere because it's very, very sensitive data. And so you have to have some kind of guarantees in place that there is absolutely no possibility that those data can leak out, that they can be shared. And it's not just, you might say, well, it goes into the hardware platform and maybe the hardware platform gets completely erased because, hey, it's qubits and they're going back into superposition anyways. But what about all the infrastructure between the compute resource and wherever your problem was generated, the networks you're trying to protect? That entire infrastructure has got to be locked down in all sorts of ways. And then the cost is not just the price of paying for the compute resource, but it's also the cost of maintaining all of the pieces that are in this. So for me, it's basically just an engineering problem of scaling it up and making it bigger, whatever. And if you have multiple compute resources, you could share them. You could have multiple ones. There are stitching procedures, stitching algorithms where you can partition your problem and then solve it on many different solvers and then stitch your results back together. But again, for me, it's the real issue are all these other moving parts, let's call them the boring parts of system development.
Thanks so much, Tom. I really appreciate the presentation. I know we're running a few minutes over time, and so I want to be mindful of everyone's schedules. Thank you again. As folks had Tom's contact information, if there are any follow-up questions that you have, or you can reach back out to ATARC, and we're happy to connect you with Tom. So any additional questions you guys might have about the technology and the work that Ridgeback Network Defense is doing utilizing quantum computing. And with that, I'd like to thank ATARC's Quantum Working Group and the folks who came to this talk, and we appreciate it. Have a great day.
Okay.
Thank you very much.
Thank you. Thank you. Bye-bye.
Great presentation. Thank you.
Thanks.
Thank you.
Appreciate it.